beautiful place for the conference. And in particular, I would like to thank Daniel for inviting me, because I'm actually not a quantum person. So I'm not working in quantum information and entanglement, even not really in quantum dynamics. I'm a mathematician, and I'm working in bilinear control theory. So what is bilinear control theory? It's a particular branch of control theory, and we are interested in systems of the following form. If you would like to impress people, you would say we are working on right or left invariant systems on Lie groups, on finite dimensional Lie group. But usually we have a matrix representation, and so the systems are of the form x dot equal to a plus u b x of t, and t of x is simply some Rn. And A and B are some n by n matrices. Of course, you can have more than, this is usually called the drift term. Of course, you can have more than only one control term. And what you usually should do, the first thing to analyze the controllability properties of these dynamical systems, you should consider the corresponding group lift, which then looks of the form capital A of x dot is equal to a plus u e b x of t, and capital X of t now is some n by n matrix. So let's choose it in the corresponding group of invertible n by n matrices. And once you know how this system behaves, you immediately know how the induced one behaves. That's the idea why one should consider this lifted system, this group lift. And of course, you immediately see, if you choose A and B to be Hermitian operators, and you put an I in front of it, and then you obtain a familiar equation of, well,
There's a bigger piece.
I prefer that one. Okay, so I H0 plus I, put that I in front. U E H1 U of t, and now U of t is something in the corresponding unitary group. And usually you consider it as the initial value, x of 0 should be the corresponding identity. So you end up with your, I would call it the lifted Schrödinger equation. Now, oh, okay. So that's what I'm trying to explain to you. First, I will give you a rough overview of the goal of the talk. And then I will discuss the finite dimensional case, and I will sketch some of the proofs in the finite dimensional case, because I think one has to see the ideas in the finite dimensional case behind the proofs to get an idea how to pass to the infinite dimensional case. Here, this will be a first. So this is actually old stuff. So that's invented around the 70s by people like Turchevich, Sussman, Brockett, and so on. This is much newer. This is a beautiful result by Michael Keil, presented for the first time 2019 at the CDC in Nice. And this is something a bit more, or this is, so to say, the new part, which is a collaboration, so to say, with Michael. So what is the goal, or what is known in the finite dimensional setting? So let's start with your standard Hilbert space, with the, so to say, lifted Schrödinger equation. And here you have your control Hamiltonian. Here now you have more than one drift term, but that's not that important. And let's stick to the simple case that our controls are piecewise constant. Of course, in the finite dimensional setting, you could choose here any kind of L1 control, and you would get perfectly solutions. But since in the infinite dimensional setting, this is a good way to guarantee solutions, we can stick to that setting here in the finite dimensional case also. And then what people have shown is that the set of all, so to say, control and drift Hamiltonian. So you put everything into one m tuple, so to say, and the set of all these m tuples such that the corresponding system here is controllable. This set is a generic subset of the set of, here, this is the that's the corresponding Lie algebra. So this is a set of two Hermitian matrices. So what does it mean? And of course, you have immediately a corollary, which makes things maybe easier to understand. Choose any pair of finite dimensional Hamiltonians, H0 as drift and H1 as control Hamiltonian, and you can guarantee that your lifted Schrödinger equation is not any, but it's a generic property. So if you choose two randomly, you end up with a system which is controllable. And that's a pretty nice.
Controllable means the solution exists or more?
More, much more. I will come to that in a moment. So sorry for that. Okay. And here, that's your question. What means controllable? Controllable means that the set of all states on your unitary group, which you can reach from the identity, is the entire unitary group. So you can go, and you are only allowed to go forward in time, not backward. But nevertheless, controllability means that you can reach the entire unitary group. And so the statement says, choose randomly a pair H0 and H1, and you have this controllability property. And you can guarantee this for a pair, then of course you can guarantee it for any n tuple with m greater than 1.
But it might take a long time. I mean, you don't have a limitation on time.
There's at least the proof doesn't give you any bound about the time you need. That's true. And then a short comment about this terminology of being generic. So this control, the property to be controllable in means is then it is phrased in this genericity terminology, which means so that the pairs where you have controllability are the set of all pairs is a generic set. There are two different interpretations. One means that the complement has measure 0. This is the sort of the genericity in the measure theoretic setting, and there's also a term of genericity in a topological setting, which means that the complement is meager. It's a meager set. And I prefer to stick to the second one, because later on, once we are in infinite dimensional spaces, it's not such a good idea to work with measures and sets of measure 0. So therefore, the topological setting or the topological terminology of genericity is maybe more appropriate. Both are invented to express the same, in the sense that the good set is a big one and the bad set is a small one. Here you can read the precise definition. What it means to be generic. It means that the complement is meager, and the set is called meager if it's a countable union of nowhere dense subsets. So the set itself can be dense. A typical example is the rational numbers are a meager subset of the set of all real numbers. So the real numbers or the irrational numbers are a generic set. The rationals are a meager set. And often it is simplified simply by saying, once you can show that your set of interest is open and dense, then you are in business. Okay. And our goal is to generalize this to an infinite dimensional setting. Now you H0 is allowed to be unbounded. The controls, they should be still bounded. And we want to get a result which says something like, here we, so to say, here we separate, we separate the drift term, and we say only we want to have conditions on H0 such that for a generic choice of control, now you get controllability. That's the idea. So we fix the drift Hamiltonian, of course, with as weak as possible conditions. And then we say within this class, if you choose then a the control Hamiltonian, you will get controllability or generic controllability. Okay, that's so to say the goal. So let's start with the finite dimensional setting. And let's recall this standard result about controllability on the unitary group. It's a Lie algebra, it's a so-called Lie algebra rank criterion, which says take all your Hamiltonians, or you should choose I times the Hamiltonian to be in the corresponding Lie algebra of skew Hermitian matrices. Compute the Lie algebra generated by all these guys. And if this Lie algebra is the entire Lie algebra of SU, then you have controllability on SU. If it's only the Lie algebra of, okay, then you have controllability on UN. If it's only the Lie algebra of SUN, then you have, of course, controllability of SUN. And the result, as I said, is pretty old, and it goes back to people like Chuchevich, Sussman, and Brockett and so on. Unfortunately, Brockett died a couple of months ago. These two guys are still alive. Okay. Now, how can you obtain, so to say, from this criterion controllability, or it's an if and only if condition, and how can you prove from the knowledge that you can generate the entire Lie algebra, how can you show that your system is really covers the entire unitary group? I sketched that very briefly because we have to use these arguments later on for the genericity stuff. Of course, you define something which people in control theory call the system group. That's the group which is generated by all these one parameter groups. So it's different to the reachable set because now T can be positive or negative. For the reachable set, you restrict to positive T. That's, of course, a subgroup of the unitary group. Then let's assume that taking the closure of this group, the closed subgroup of this Lie group, which is itself a Lie group, and let's assume that the closure of this subgroup, the corresponding system algebra is UN or SUN. Then, of course, you can immediately see that the group here is all. It's a, we know the closure of these one parameter subgroups gives you a closed subgroup, and a closed subgroup has a Lie algebra, and according to this condition here, it is easy to see, since all these one parameter subgroups here are contained, this is simply an approximation argument to see, okay, here you can choose V to be 0, then of course H0 is in, and if you let T go to 0, and if you blow up V, then you can also see that all the other one parameter semigroups are in, and then you immediately see that generating or computing commutators, the Lie algebra, the generated Lie algebra by these terms will give you the Lie algebra of the generated of this system group, and if this is big enough, you know, you have everything. That's the idea. But how can we pass from Now we know that the group generated is everything, but we want to see that the reachable set is everything and not the group. And in general, you cannot conclude from the Lee-Archer rank condition that you get everything. Here you can, simply due to the fact that UN and SUN are compact. And you choose, now you restrict yourself to positive T, so to the reachable set, which was defined here. And it's easy to see that this reachable set is itself a sub-semigroup, the semigroup, of course. By the construction, you have one time evolution and then you concatenate with another time evolution. So it's a semigroup. And once you take the closure of this one, it's no, that's the wrong direction. So once you take the closure of the reachable set, you have a closed sub-semigroup. And then there is this beautiful result which says that in compact groups, there are no proper closed sub-semigroups. All closed sub-semigroups are already groups. If the group you are sitting in is compact. So the group itself is compact. Taking the closure of the reachable set, you get a compact sub-semigroup, and compact sub-semigroups are already true groups. And that you have to know at that point. And it's actually not very difficult to see. Let's start with a simple example. Let's choose G to be a finite one. Let's assume that this is a finite group and that S is a semigroup. A semigroup of this finite one. And there are the same holds. There are no proper semigroups in a finite group. Why? All you have to show is that if you choose any element in here, let's call it G, you have to show that this has an inverse in this set already. So take any power of G, and since it's a finite group, you know there's an N1 and an N2 that these coincide to the finiteness. And this gives you, let's assume that N2 is greater than N1. This gives you that G to the power N2 minus N1 is the identity. And this here is positive. So this guy is in your semigroup. And then you are done. And you have an inverse of G. And the same can be done in the compact case. Now let's assume that this is a compact group, and this is a closed subgroup. Now you do the same trick. You consider C to the N, and do the compactness of this guy. You know there is a convergent subsequence. Not the entire one maybe, but there's a convergent subsequence. So in G to the power of NK converges to some element H, okay to infinity. And now you play a similar trick by saying, okay, let's choose NK plus 1. This is in the index times G NK, and let's see minus this one. And now this does converge. This one does converge to G. This one does converge to G. So together it converges to minus G. So this is again E. And now here, this is the fact that the exponent here is bigger than 1, bigger or equal than 1. You see that this is again in S, and you obtain your inverse. So this says
Sequential compactness.
This is sequential compare. That's a good point, but it's also true if it's a topological group. And you have to know that in a topological group, you have by assumption the multiplication is continuous, and the same result holds if this is not sequentially compacted, it's really compact if you have some weird topology. That's true. Yeah, anyway, so you know that the closure of the reachable set and that the closure of the system group, that they actually coincide due to this argument. For the closure of the system group, we already know that it's everything. So we know that the closure of the reachable set is everything. So only what we have to do is we have to get rid of the closure. In finite dimension, one wants to get rid of the closure. In infinite dimensions, you shouldn't do that. But in finite dimension, you can do that due to the fact what the Lie algebra rank condition is actually good for is that it says in any setting that the reachable set has an interior point. So usually the reachable set, if you start here at the identity, this is the reachable set, and then you have an interior point. And on the other hand, you know that your reachable set is dense in the entire space, so there is no problem to shift this neighborhood or this open set to the identity, and once you have an open set of the identity in your reachable set, you are done. So that's the idea behind this. Well, that's one way how to prove this. Now let's come to the genericity proof. How did they do that? Okay. First note that we can stick sorry, we can stick to the case m is equal to 1. If the if it's true for m equal 1, it's true for m equal bigger than 1, of course. So now they look at pairs H0, H1, such that that's of course, so you let act H0 by the joint operator on H1. I guess I don't have to explain the notation here. So at K H1 is nothing else than the commutator of these two guys. And then you compute iterated commutators. This is an invariant subset. It's sitting in the corresponding Lie algebra of skew Hermitian n by n matrices. And I claim if this invariant subset has dimension n square minus 1, I'm done. Why? So without loss of generality, we can assume that H0I is diagonal. And H1 this can be any full matrix. Okay. But if I start taking computing commutators between these two guys, I get the following structure. I get zeros on the diagonal and something here and something here. How much is this something here and something here? It has dimension n square minus n. So if I can guarantee that I have all of these matrices in the Lie algebra, the remaining ones can be easily generated by taking further commutators between some elements here and some elements here. So all I have to guarantee is that this span is everything to see that the pair H1 and H0 yields a controllable system. Now, how can I prove that the pairs with this property that this here has dimension n-1. How can I prove that these pairs are open and dense? And then I'm done, because then the set of controllable systems is a generic system. There are different ways to do that. Maybe one is the easiest one, maybe, I don't know. But let's see, at least the one I know, and therefore it might be the easiest one. We define a map from this pair to this guy here. So how should you think of this? So these are vectors. If you choose a basis of your Lie algebra, these are vectors of size n square or n square minus 1, depends on whether you're in SUN or in UN. And so you have n square minus 1 of these vectors of length n square. And now you pick, so you can visualize this as a matrix of this size, and now you pick all positive square minus of this rectangular matrix. And this is indicated here in that way, so that you choose here. This is a multi-index, which says which rows you should choose. And this defines you the map P index I, and then you collect all the minors. Now you have this map P H0, H1, which says here you have here the determinant of the first minor, you have here the determinant of another one, and so on. And if you put in combinatorics, you can easily compute how many of these minors are there. So this is a map now from your pairs H0, H1 into some huge Rn. So the map goes here in some huge Rn. And I claim H1, H0, H1 satisfies G. What was G? G was this condition, or actually this condition here. No, it was this condition, the dimension. It satisfies this condition if this is not the map, if this is not completely zero. Because if this is not completely zero, one of these n by n minors, let's assume this one, the determinant of one of these n minors is different from zero, which means that this block here, so to say, is invertible, but this immediately implies that the entire set of vectors has full rank. Okay. This, of course, then is a map. It's a polynomial map in your entries here. And the converse of this condition. So what about the inverse set of zero, so to say? So what can we say about the set such that this map here yields a huge zero? This is an a nowhere dense closed set. So the complement is an open dense. So the complement is an open and dense set. The only case we have to exclude is it could be everything if this polynomial map is the zero map. Then we are in trouble. But this you can exclude by simply choosing one clever example which shows that there is one pair which is controllable or which satisfies condition G. And if you have one pair which satisfies condition G, do the polynomial structure of this P, you know, the set which violates this condition has to be meager or has to be nowhere dense and close. So that's the strategy how to prove the genericity result in finite dimensions. How much time do I have?
Slightly less than 20 minutes.
Okay, that's fine. So
One question.
yeah, of course.
How many commutators do you need for your pair? to get the Hermander condition. This is sometimes also called Hermander condition, right?
Yeah.
How many commutators do you need? Huh?
I guess in
N. My student fought very hard. He can prove it in log n
it depends on, of course, if you,
generically.
I don't know an answer from the top of my head.
There's some recent work on this. I can dig out the reference.
That's my student. That's why I'm log n. So
Yeah.
I find it very, I mean,
It could,
log n is enough.
if you stick to taking only commutators, with the first one is H0 and the other one is, then of course you have to take n minus n square minus 1.
Yeah.
But you want to choose
We are choosing
arbitrary
H0,
commutators.
H1, I mean, and then he could prove you can do it. You need log n many commutators.
But I think the person I'm thinking of is a she, so maybe there's
And
some.
it's independent. Interesting, yeah.
Okay. So let's come to this first infinite dimensional result, which is actually by Michael Keil. There are a couple of works. There appeared a couple of works before the one by Michael from the French side, Hugo Boscain, Mario Sigalotti, and so on. And I think they had quite similar results, but the brilliant part by Michael was to give this to give their proofs a beautiful structure which can be easily absorbed, so to say, by a mathematical physician.
Mathematical physician.
Physician, not physician. Sorry for that. Nobody realized that. Except you. Okay. Yeah. So our. Okay. Yeah. Okay. First, let us discuss the right setup. And if we heard before by Paolo, it might be a good idea. What is the right topology to choose on the unitary group? And the right one seems to be the strong topology. Of course, if H0 is unbounded, the corresponding one parameter group is only a strong one parameter group and not a uniformly one. The set itself has still a nice structure. It's still a topological group with this strong topology, and it's still metrizable due to the fact that it's a bounded subset of the set of all bounded operators. Usually these topologies are not metrizable, but since this is a bounded subset of the set of all bounded operators, you can metrize. There's a metric which yields the same topology. It makes some proofs easier. You can work with sequences. And the other point is that if you would choose the uniform topology on your unitary group, there were no chance to get approximate controllability, because you can easily see, I think, by the construction of these one parameter semigroups, that the reachable set, the closure of the reachable set, is separable in the sense that it has a dense countable subset. Simply evaluate your one parameter semigroups at the rational numbers or something like that. However, if you choose the uniform topology on your unitary group in an infinite dimensional Hilbert space, this is no longer a separable subset. So in the sense that there is not a countable subset, such that the closure of this countable subset with respect to the uniform topology will give you everything. And the easiest way to see this is simply restrict to so to say, to infinite diagonal matrices. So choose a basis in your separable Hilbert space and consider, let's say, this subset of your unitary group. And this subset is obviously, it's not really the same as L infinity, but it sits in L infinity and it's a non-separable subset in L infinity. So you have a non-separable subset in your unitary group with respect to uniform topology, and this immediately tells you that's not such a good idea to choose this uniform topology, because then you would never get controllability in an even not in an approximate sense. Okay, now these are the standard assumption which Michael made. H can be possibly unbounded, everything else should be bounded. And let's see how far we can go. And here, of course, choosing only piecewise constant controls immediately guarantees that you have no problem with any with the existence of solutions. Yeah? So I think we can skip that part about the solution concept, because it's clear if you choose here a constant one and this is bounded, this is again a self-adjoint operator and so on. I don't have to tell you that. Okay. Then he imitates the definition of the finite dimensional case. There's only one last item where he slightly deviates, and this was the interesting part, how to deviate from this Lie algebra you usually associate. Usually you associate a system algebra in the finite dimensional case by saying, let's look at all at the Lie algebra generated here by these guys. And of course, you immediately see if this is an unbounded operator, it's not a good idea to replace this simply by taking commutators and this Lie algebra. So you have to refine, or you should refine that. This was the strong reachable set, which is the smallest strongly closed sub-semi group. Of course, it's a sub-semi group, then the closure will be again a sub-semi group of U, which does contain all these one parameter semi-groups. Then the system group, it looks quite similar. The difference is again here by here restrict U. Here you have to restrict to t greater than 1. And you say that your system is strongly approximately controllable if the reachable set is, and the reachable set is already defined as the strong closure of the ordinary reachable set, if this coincides with your unitary group. And here comes the new idea of Michael to say, let's define the system Lie algebra as the set of all bounded, now all bounded skew-Hermitian operators, such that the corresponding exponential is in the system group. So he wants, so to say, calculate the Lie algebra of the system group. But he does allow only bounded operators for this associated Lie algebra. And in principle, so far, from the definition, it's not clear that there's anything in. It could be empty. No, not empty, but 0. But this was his first result, and maybe I have to speed up a little bit. This was his first result where he proved that, again, all these one parameter groups, and H is running from 0 to M, all these one parameter semi-groups are in the system group, and the Lie algebra, here the dynamical or the system Lie algebra is a strongly closed Lie subalgebra of the skew-Hermitian operators, and it does contain at least the group not the group, but the elements here for h equal to 1 up to n. Not h being 0, because this was the unbounded operator, but all the others are again in. Okay. And for proving this, you need a kind of continuity result for the exponential map with respect to the strong operator topology, but this can be found in the literature. I guess we can find everything in that direction in Reed-Simon or something like that. So then he imposed a further condition on the unbounded part by saying that it should have only point spectrum. So the entire spectrum is given by the point spectrum. There are no other points in the spectrum. At that point, you don't have to require that they are isolated, but all of them are really eigenvalues. And with this additional assumption, he could prove that the backward evolution of the unbounded part is also in the system group. And that's not that difficult, I think, to see. The idea is at least you choose a basis for your an eigenbasis. And then in its eigenbasis, your unbounded H0 has the form λ1, λ2, λ3, and so on. And then you have to see that the closure does contain the backward drift. Yeah? And all I think you have to do is, in principle, you have to cut out these parts and you have to use the corresponding finite dimensional result. 5 minutes, okay. Okay. So this shows that you have the backward drift in. Then you can construct or you can associate to your H0 and maximal torus. That's, I guess, it's a standard construction, but you have these spectral projections. So far, the eigenvalues can be still degenerate. So you have these eigenprojections. You consider the complex span of these eigenprojections and take the strong closure that's denoted by E of H0. You intersect them with the unitary group, and this gives you the maximal torus in finite dimension. If this is to see what happens in finite dimensions, if λ1 is different, if all these three are different, so the maximal torus is of this form: e to the I phi1, e to the I phi2, and e to the I phi3, where phi1, phi2, and phi3 can be anything. And so he's imitating this construction, and this maximal torus has this neat alternative description. And there, since this is a double commutator, you immediately see it's a von Neumann algebra. And so it's a abelian von Neumann algebra. So you could think for a moment, what can it be? I think there are three different types: the big L infinity, the small L infinity case, and the finite dimensional case. Or do I miss anything? No. Okay. So yeah, and of course, and in this case,
There are sums of those.
yeah, of course, that's yeah. So I missed something. All right. So, and in this case, you are faced with the small L infinity case, and again now imposing an additional non-rationality condition on the eigenvalues will show you that the entire torus is in your system Lie algebra. The entire torus is in the in the group, in the system group, and from there you can then conclude that the corresponding, if you consider this on the algebra level, that you have all these projections, or I times the projections in your system algebra. And this is why this result is so beautiful, because now at the very beginning, if you do not, so if you try to imitate the finite dimensional case by brute force, you would write here 8IH0, but IH0 is not a good idea. But now we have all these bounded, these bounded spectral projections in, and now we can consider this Lie algebra, and now we can check whether this Lie algebra is everything in the strong closure, and then we are done. And that's exactly what you get if you impose a further condition which says that you want to have this, that the eigenvalues are all simple, they are non-degenerate, and then you need a kind of connectivity graph, which I would say in the simplest case you can read that. And it simply says more or less, if you have only one control Hamiltonian, it says that there shouldn't be too many zeros in. So the best would be that all off-diagonal entries are different from 0. Because then you can immediately start commutators, taking commutators with your, then now with these conditions, now that's the final result of Michael, you end up with controllability of the system. And the idea is simply, and I even adopted my notation to your language, that's these rank 1 projectors, and now you compute commutators between, let's say, H1 and your rank 1 projections, and you see immediately with these commutators, finally you can fill the entire Lie algebra. And then taking the closure, you are done. And I'm also almost done. This is the result we want to prove, or we are dreaming of. So the conditions on A are here, on H0 are here. Again, the standard condition on A about that, of course, it was nothing else than it's a self-adjoint operator. And here we had to impose a slightly stronger condition than only pure point spectrum. Here we additionally require that this pure point spectrum is discrete, so that you have no accumulation point. Right now, these accumulations points, they really bother us. So let's assume that you have no accumulation points. And finally, I think this is missing here. Finally, you want to have that all the eigenvalues are still simple. Maybe one can get rid of this also later, but at that point, we have to require that they are simple. And now what is the idea? And maybe I stop at that point. How? Because now we have no irrationality condition so far, which was very important to get the entire torus. So after lunch, you can play with the following example. You start with 1, 1, 1, 2. That, of course, doesn't satisfy the irrationality condition. And then you add up U 0, 1, 1, 0, and you compute the eigenvalues λ1 and λ2, and they will be rationally independent for almost all U. So the idea is to use the bounded control Hamiltonian, to add the bounded control Hamiltonian first to the unbounded drift Hamiltonian, to guarantee that you get something which fulfills the irrationality condition, on a huge set. And then you have all these tori in, and then you pass to the limit u equal to 0, and then it's not too difficult to see that these tori, that they converge to the torus, the full torus of H0. That's the idea. And the genericity argument comes in that the set of control Hamiltonians H1, where this procedure works, should be again a generic set. I thank you for your attention. Sorry for being a little bit late, and I hope you can still enjoy your lunch.